Alright, hello class. In this video we are going to be talking about techniques for calculating limits. So as we established last time, things like graphs and tables are only going to get us so far. In fact, those are probably, especially tables, are most likely the worst possible way we could try and figure out limits. And part of the reason for that has to do with, well, how close we have to get. And tables, there's all sorts of weird things that could be going on. And on graphs, it can sometimes be hard to tell what's going on. You might have to get really close to see what's happening. So what do we do, and what techniques do we have that are way more efficient for calculating limits by hand? That's what we're going to talk about in this particular video. First, I want to start with an example to show why we need a bit more than what we have so far. All right, to show you an example of why tables aren't a great way to go about doing this, let's suppose that we are looking at the limit as x goes to 0 from the right of sine of 1 over x. Okay, I'm going to set up a table to see what's happening here. And we could pick things like 0.001, 0.0001, 0.0001, but instead what I'm going to do is I'm going to choose x values that play nice with sine. Okay, so this is just for demonstration purposes, but we'll choose values that play nice with sine and go to 0. Okay, so what values would play nice with sine? Well, anything with a pi in it, right? So what I'm going to do is, let's say I'm going to let x be 1 over pi, 1 over 2 pi, 1 over 3 pi, 1 over 4 pi, etc. Right? We'll just continue on in this manner here. Now to show why that, say, goes to 0, well, what we're doing is dividing 1 by larger and larger values, and if you use your calculator, these are the if you use your calculator, these are the values that you would get. Okay, I realize in the first one I skipped 1 over 5 pi, but here's the values. We have 0.3, 0.1, 0.106, 0.07, 0.06, 0.05, and then I went all the way out to 1 over 100 pi, which will be 0.0031. So we are letting the x's get closer and closer and closer to 0. We're just doing it in a funky way, and specifically a way that plays nice with sine. And the reason we want to do that is because, well, sine of 1 over any of these, say 1 over pi, let's say. Well, when we invert and multiply, that's going to be sine of pi, which will be 0. Okay, and if we do this with any of the values we just gave it, say 1 over 1 over, let's say k pi for any of these values. We invert and multiply, we'll get sine of k times pi. Any multiple of pi will give us 0, and this is provided k equals 1, 2, 3, 4, any of these whole numbers. Right, up to 100, on and on and on. So when we fill out the table, every one of these x values gives us 0. Okay, so we would expect that the limit as x goes to 0 from the right of sine of 1 over x will actually equal 0, because everything we're plugging in as we get closer to 0 gives us 0. So that's what we would expect. However, we'd be wrong. If we change this and maybe choose new x values, right? So let's put a 2 over all the values we had before. So something like 2 over pi, 2 over 2 pi, so that would just be 1 over pi. Okay, so let's do 2 over just the odd numbers, so 2 over pi, 2 over 3 pi, 2 over 5 pi, 2 over 6 pi, 2 over, not 6 pi, sorry, 7 pi, 2 over 9 pi, 2 over 11 pi, and let's go all the way out to 2 over 99 pi. All right, and using our calculator, we'll get the following values. Okay, we'll get these values. So once again, we're still getting closer and closer and closer to 0 here. We're just, again, doing it in a way that plays nice with sine. But when we plug any of these values in, let's say sine of 1 over 2 over pi, when we invert and multiply here, we'll get sine of pi over 2. Sine of pi over 2 is 1. Oh, okay. Then if we put in sine of 2 over 3 pi, whoops, we get sine of 3 pi over 2. Now, sine of 3 pi over 2 is negative 1. Okay, then sine of 1 over 2 over 5 pi, we invert and multiply, gives us sine of 5 pi over 2, which is back to 1 again. So our sine value, sine of 1 over x, when we match it up, we're going to get 1, negative 1, 1, negative 1, 1, negative 1, on and on and on and on. Okay? So from here, okay, for x is equal to 2 over k pi, where k is odd, okay, or you could write k is 1, 3, 5, 7, etc., right, all the odd values. Our signs oscillate between negative 1 and 1. This isn't possible for a limit to exist. So in this case, this means the limit as x goes to 0 from the right of sine of 1 over x does not exist, because oscillating precludes, I guess that's the right word, precludes your ability to be able to get closer and closer to a single value. So, all right, so the limit as x goes to 0 from the right of sine over 1 over x cannot exist, because sine of 1 over x does not get closer to a single value as x gets closer to 0 from the right. And this is because, well, sine of 1 over x oscillates between negative 1 and 1 and hits every value in between and 0 and everything else. Okay, however, if we had stopped here, we might have thought that this limit was 0. Okay? So it's possible that a table can lie to you. All right, now let's look at a graph and see what story it tells us. Okay, so here is just the graph of y equals sine of 1 over x, and it doesn't look, well, maybe it does look very strange, but here, as we're getting closer and closer to 0, what you'll find is that we just get a whole bunch of oscillations. So it doesn't matter how close you're able to get. Right here, I can zoom in on the x-axis, but say not the y-axis. If it will let me, there we go. Sort of slowing it down some. But your graph eventually just starts looking like just this solid band, because this graph starts oscillating between -1 and 1 so fast, right? It just looks like a big smudge. Okay? So, this is why graphs and tables aren't enough. We need more techniques to help us calculate limits. Okay, so let's talk about what those techniques are. Okay, so the very first technique we're going to talk about, it's essentially that if you can plug in a value, like if you can plug in the designated value and get something out with no problem, then that's it. All right, there's nothing really extra to do. Right, so we've sort of already talked about this, because this is another way of saying that if f of x is continuous at x equals a, then the limit as x goes to a of f of x equals f of a. All right, so to give an example of that, if we're talking about the limit as x goes to 2 of, let's say, x squared plus 1 all over x minus 1. Okay? Well, there shouldn't be any problem here, because if we just plug in 2, right, which would give us 2 squared plus 1 all over 2 minus 1, this would give us 4 plus 1, which will be 5, and 2 minus 1, which will be 1, and we get 5. Well, if we can do this, and there's no issues, then this is your limit. Okay? Now, this is exactly the same thing as if I said f of x equals x squared plus 1 all over x minus 1, and I told you to find f of 2. F of 2, you would do the same thing, 2 squared plus 1 all over x minus 1, and that would give us 5 over 1, which is 5. Okay? It's because this function is continuous at 2, its value and limit are the same. All right, so again, since this is continuous at 2, the limit is equal to the function value. That's what I call the f of 2. So the limit at 2 is equal to f of 2 because the function is continuous there. That's what this first technique is all about. And this is the one that you should probably always start with, unless it's obvious that what you're dealing with isn't going to work. Okay? Because if you can just plug in the value, just plug it in and move on. Right? Now, I could go into a lot of detail about why this is true, but if you look back at the other examples, or you start making tables, or you start looking at graphs, you kind of start to see that, oh, if the function's continuous, we really don't need the limit, really, if it's continuous, because we can just plug the value in and see what it is. Limits really start to shine when we start looking at 0 over 0 cases. Okay, so for 0 over 0 cases, and this is where we really want to use limits. So for these indeterminate forms, for the limit as x goes to a of f of x, if f of a yields 0 over 0, then use algebra to simplify f of x and try again. Right? So if we get a 0 over 0 spitting out, we're going to want to use some sort of algebra to simplify. Okay, well, what sort of algebra? Well, the most common techniques are things like factor and cancel. So I'll just say factoring, what's called conjugating or conjugating factors. Okay, fraction arithmetic is a big one. Okay, and others, right? There are lots of algebra techniques that we can apply. We just need to simplify f of x. And by simplify, okay, we mean get rid of the thing that's causing the 0 over 0. Right? So let's look at an example, and I think hopefully it will start to make some form of sense when we start doing these. All right, so let's look at this example here. We've looked at this one before in one of the previous videos. All right, so we're talking about the limit as x goes to 1 of x squared minus 1 all over x minus 1. Okay, so we've already looked at this one, but in the past, okay, if we were just shown this thing here, what we often would do is just say factor everything, right? Factor the top, cancel out that piece, and then just say that this is equal to x plus 1. And we actually saw that the graph of this looked exactly like the graph of x plus 1. However, there is a difference between these two. Okay, the big difference is that here x is not allowed to equal 1. Whereas here, if this is what we started with, x could be anything. So we have a hole at x equals 1. Okay? So this is exactly how we deal with a limit, though. Because if we were to plug in x equals 1 directly, we would get 1 squared minus 1 all over 1 minus 1, which would be 0 over 0. Okay, so this is a 0 over 0 case. But we tackle it in exactly the same way as we used to, except we're being a little more mathematically mature. Because here, a lot of times we aren't specifying, as we should, that x can't equal 1. We're over here, what we're actually talking about is a limit. Okay, so what I'm going to do is the limit as x goes to 1 of x squared over x minus 1 is the same thing as the limit as x goes to 1 of, we'll just factor the top. Okay, x plus 1 times x minus 1 all over x minus 1. Okay, now the x minus 1's cancel, and we're left with the limit as x goes to 1 of x plus 1. Okay, and now this is something that we can just plug directly into. That 0 over 0 piece is gone. So now we can just plug in the 1, and we'll get 2, which is what we got previously from the table. That's what we got looking at the graph before with this same example. Okay, now notice how I've written this. Right? People are very particular about this. We are saying that the limit as x goes to 1 of this thing is equal to the limit of this thing, which is equal to the limit of this thing, which is equal to some number. All right, what people don't want to see usually is this. We have the limit as x goes to 1 of x squared minus 1 is equal to, we just drop the limit signs and say this. Okay, and then we say cancel that and say that that's equal to x plus 1. There's a reason we don't like this, okay, and a big part of that is the fact that the limit is an object all by itself, right? The limit is analyzing this thing. Without a limit sign here, this is a function. This is a function and is a different value, or it's a different object. So we can't say that two different objects are the same thing. We can do it here because what we're saying is that the limit of x plus 1 as x goes to 1 is 2. We can say that because these are the same object. The limit is typically giving us a number if it exists, right? It's telling us where the function is going to. This, without the limit sign, is just the function. Okay, so that's a big notation thing that most people get up in arms about. So you got to make sure that you write your limit signs. Okay, each time. Until you are plugging this value in. All right, another reason why it's important is I'll have students often, they'll forget to write their limit signs, then they get down to here, then they're not sure what to do. Okay, where with the limit sign, okay, it tells you what to do when you get here because it's saying the limit as x goes to 1. Oh, x is going to 1, so x goes to 1. So we have 1 plus 1, which is 2. All right. I have an alternative for you there. I actually find it a little tedious to write the limit every single time. So what I propose is a compromise between these two. I understand not wanting to write the limit sign every single time. However, I have to conform to the fact that notation-wise, we do need to get out of the habit of just using equal signs indiscriminately. Equal signs are a very important symbol, and we should not throw them around if the two things are not actually equal. So if they're completely different objects, a limit versus a function, we should not use an equal sign. Okay, so my compromise notation is actually to just use arrows, right? Because what we're really saying with limits is that in this case, as x goes to 1, f of x goes to 2. So I see no problem in using arrows to as a stand-in for a limit notation. It's something I use myself in my own publications, my own research. I often just resort to arrows instead of using the limit symbol. Okay, so to give you an example, what I mean, okay, is if I have the limit as x goes to 1 of x squared minus 1 all over x minus 1, I could just say this goes to x plus 1 times x minus 1 all over x minus 1, cancel out the x minus 1s, and say that that goes to x plus 1, which then goes to 2. This is a lot more accurate than putting equal signs, okay? Because you're at least giving the impression that it's a limit, right, when you're using arrows. Okay, so just always remember the big difference. And this comes from the fact that when we're talking about f of x, say f of 1 tells us what f equals, okay, when x equals 1. But the limit as x goes to 1 of f of x, this tells us what f gets closer to when x gets closer to 1. Okay, so if you want to use equal signs, you need to put the limit sign each time. If you don't, you need to use arrows instead of equal signs. Okay, all right, I'll get off my rant soapbox now. I will say, though, don't expect this to fly with other professors. If you take Calculus 2 with somebody else, they may require you to write the limit signs. Okay, so just bear with them on that. Don't go around telling them that Dr. Denton said you could do whatever you want. That's not what I'm saying. I'm saying that I am amenable to this compromise. And in fact, I'm going to use it because I prefer this notation much more. Okay, but just expect that other professors are going to want you to use this notation. All right, let's do another example of this type. It's a pretty common type of just the factoring and canceling. So here, I have the limit as x goes to 3 of x squared minus 2x minus 3 all over x squared minus 5x plus 6. So when you plug this in directly, all right, you'll get 3 squared minus 2 times 3 minus 3, all over 3 squared minus 5 times 3 plus 6, which is 9 minus 6 minus 3, all over 9 minus 15 plus 6. In both cases, this is going to give us 0 over 0. All right, so a 0 over 0 case. Now, let me specify. Whenever you see a 0 over 0 case with a limit, do not put undefined. Okay? It might, right? It might mean that. But with limits, 0 over 0 means there's more work to do, always. Okay, and what work is that? Well, with a 0 over 0 case, it's usually algebra. And I always like to say that most of the algebra you learn is specifically to be used in calculus. That's kind of not true, but for a lot of it, it kind of is. A lot of these techniques that you learn are considered pre-calculus, these techniques that you need for calculus. All right, so since this is a 0 over 0 case, I'm going to try and factor everything and see if something cancels out that is the thing that's causing problems. So for the top here, I want two things that multiply to give me -3, but sum up to be -2. So I'm thinking x minus 3, x plus 1. And on the bottom here, I want two things that sum or multiply to be 6 and sum up to be -5. That I'm thinking is x minus 3 and x minus 2, because -3 and -2 are positive 6, and -3 plus a -2 is -5. That should do it. And look at that. Those minus 3's cancel, and also see that this is usually what happens. That thing that is causing the 0 over 0 disappears. Okay, now that does not necessarily mean the limit is going to exist. We'll see that in the next section, actually. But what it does mean is that there's something there that the numerator and denominator are sharing in some way that we can get rid of. Okay, so then we get x plus 1 over x minus 2. And now we should be able to plug in the 3 without a problem, because that division over 0 should be gone now. Right? So we should get 3 plus 1 over 3 minus 2. And now we could put in equals, but I'm just going to keep it strung together with arrows. This will be 4 over 1, which is 4. And down here you can do equals if you like. But there we go. The limit of this guy is 4. Okay, so the next technique is sort of a factoring. It's like a pseudo factoring, I guess you could say. And so it's called using a conjugating factor. And what we end up doing is whenever we see square roots showing up, and it's a 0 over 0 case, right? Because if we just plug in the 9, so say here with the limit as x goes to 9 of the square root of x minus 3 all over x minus 9, if we were to plug in the 9, you get square root of 9 minus 3 all over 9 minus 9. Well, that's going to be a 0 over 0 case. So we've got to find something to do. And what we end up doing is it's very similar to what we used to do if we were dividing by some sort of square root thing. So if you remember back if you ever had square roots in the denominator, math teachers probably always told you can't have square roots in the denominator. That's not true. You can. It's just more that we prefer to have them in the top. But also, a lot of those techniques are things that we're going to use when trying to calculate limits. So if you remember, what you would do in this case is you would rationalize the denominator by multiplying the top and the bottom by a conjugating factor, which would be, for the 1 plus square root 2, you'd multiply the top and the bottom by 1 minus square root 2. Okay, and what that would do is on the top, well, we would multiply these together. And on the bottom, when you multiply these two guys together, this is what's called a difference of squares, because you have an a plus b times an a minus b, which always comes out to be a squared minus b squared. Okay, so this is going to come out to be 2 minus 2 square root 2 all over, it's going to be 1 squared minus the square root of 2 squared. So we'll get 1 minus 2 here in the denominator. All right, so it'll be 2 minus square root 2 all over negative 1, or negative 2 plus 2 root 2. Okay, this is, so 2 divided by 1 plus root 2 is this thing right here. This is called rationalizing the denominator. You can call this a conjugating factor. We're going to do the same thing here. Okay, so we'll do or use a conjugating factor. And how a conjugating factor works, it works the same way. And it's not always the denominator. Okay, get that out of your head that it has to be the denominator. We use a conjugating factor with whatever, or with wherever our square root lives. Okay, so wherever it lives. So here, our square root lives in the numerator. It's a square root of x minus 3. So we're going to take that and multiply the top by the square root of x plus 3 over the square root of x plus 3. All right, now that's going to go to, we're going to multiply these guys out. So we're going to want to FOIL this. Okay, and here, the other part, you're going to want to leave alone. So in this case, don't multiply out the denominator. Okay, so wherever the square root lived, that's what you mess with. Wherever it doesn't, originally, don't. If you FOIL both, you're just going to be in a messy place, because here, when we FOIL this, let me break this off a little bit. Remember, the a minus b times a plus b, that's going to be the first term squared minus the second term squared. Okay, and again, I'm going to leave the denominator alone. Okay, which will simplify down to square root of x squared is x minus 9, so 3 squared, which is 9, all over x minus 9 times the square root of x plus 3. Okay, and now the x minus 9s cancel, and this is why we don't mess with the denominator. Probably the two biggest mistakes I see of this type of limit are people either just not knowing how to do this part, right? Or they don't change the sign. They don't make a minus into a plus or a plus into a minus. Or they will FOIL both, and if you do that, you won't see this cancellation. Okay, and then another common mistake is, keep in mind, when these two cancel, we still have a 1 on the top. Okay, and now we're left with 1 over the square root of x plus 3, and we can just plug in the 9 now. Right, so here we go. Let's plug in the 9. We'll get 1 over the square root of 9 plus 3, which is going to be 1 over 3 plus 3, which is 1/6, and there we go. Now, some of you may have been screaming at the screen, wondering why I was going through so much trouble with this one, when you are saying that you could actually factor this. Dr. D, you can actually factor this, and yes, you can. Some students preferred this method. However, it's still good to know how to do that conjugating factor, and I'll show you in the next example why. But yeah, this can factor, because if you're looking for things of this form, a squared minus b squared, which will factor into an a minus b times a plus b, right? This difference of squares, which is really a good method to know, okay? For the difference of squares, you can actually think about x as, let me use the arrow here. We'll leave the numerator alone, but you can think of the denominator as the square root of x squared, right, because that would give us x, minus 3 squared, right? So technically this is a difference of squares, it just doesn't look like it at first. Okay, and this would factor into the square root of x minus 3, okay, all over, and since it's the difference of squares, it'd be the square root of x minus 3 times the square root of x plus 3. Right? So that would factor, and we'd end up with 1 over the square root of x plus 3, which is exactly what we got last time in way fewer steps. Okay, especially if you don't need this part, if you just know that this can factor. So this will still get us down to 1/6. Okay, well, yes, that's perfectly fine. If you're comfortable with this and you like doing it this way, by all means, you can still factor with square roots. However, it's still probably a good idea to know the conjugating factor for situations like this next example here. Okay, let's say we're looking at the limit as x goes to 1 of x minus 1 all over 4x plus 5 square root minus 3. Okay, so when you plug in the 1, you get, of course, 1 minus 1 all over, this will be 4 plus 5 square root, which will be the square root of 9 minus 3. That's another 0 over 0 case. Okay, so yes, we can factor this possibly in a way to make it look like this, but it's not going to be completely routine, right? So this is where we're going to want to use a conjugating factor because I see some square roots. Okay, so all I'm going to do is if I see square roots and I don't either know how or I'm not comfortable with factoring non-squared things, okay, what I'm going to do is set up a conjugating factor. So I'm just going to take the whole 4x plus 5 square root. Notice the sign does not change there. We don't mess with what's underneath the square root. Plus 3. Let me put that on both the top and the bottom. All right. Now let me clean this up. Okay, so now we'll just start working through this. Now we don't have to do a lot of work foiling the bottom because we're just going to use the difference of squares idea, that an a minus b times an a plus b is an a squared minus b squared. And we're going to leave the top alone, right? So we leave this part alone. Be careful with your parentheses. It's a good way to get a wrong answer. Not careful. And then here, it's just going to be the difference of squares. So it's going to be that first term squared, so that will be 4x plus 5, minus the second term squared, which will be 9. Okay, so we're going to get an x minus 1 times the square root junk on the top, so leave that alone. Okay, so I put the notes here. Where the square root originally was, we're going to FOIL that, but we're not going to FOIL this. All right. So here, this simplifies now to be 4x minus 4, okay, in the denominator. And we can actually factor out the 4. Let me go ahead and do that. So we'll get 4 times x minus 1, and there it is. The x minus 1's cancel. Okay, and then we're left with just the square root of 4x plus 5 plus 3 all over 4. And now we can just plug in the 1. Right, plugging in the 1 will give us the square root of 4 plus 5 plus 3 all over 4. So that's the square root of 9. So that's going to be 6/4 or 3/2. Okay, so yeah, even if you're good at factoring and you can factor even when you need to get down to square root terms or lower, it's still a good idea to know how to do this conjugating factor because it will pop up in more places than you might expect. Alright, so I am going to go ahead and put a cut in this particular video and then come back in a part 2 to show some of the more examples of different algebraic techniques that we can use. Alright, and I'll catch you all on that one. Cheers.